Started at Intel years ago doing the user mode setting work and then the gem graphics memory management. And more recently, I've had a lot of fun working up in user space again, finally, where debugging is a lot easier. So I'm going to talk real quick about what we've been developing for the last year or so. Major changes in OpenGL. Major changes again in the 2D driver, looking at a new acceleration architecture called SNA, or another new one called Glamour. Some of the work that's been going on in CairoGL that I talked about here 2 years ago. I think 2 years ago, yeah. And then what we're doing in LibYurm for debuggability. So the big news, I think, in Intel graphics right now is that we are hoping to release OpenGL 3.0 tomorrow. This has been the culmination of about 3 months of serious work after a bunch of prep work that had been going on for the last year or so. But we made the decision we were finally going to ship OpenGL 3 and do all the work required. And it came almost in to our original schedule. Kind of amazing. So OpenGL 3 is a collection of new features. And for a lot of open source developers, that collection of new features doesn't sound that interesting. There's a lot of stuff for, building more advanced 3D first-person shooters and stuff that probably a lot of us don't care about. Actually, I think the more interesting part of OpenGL 3 is that it provides a lot of new guarantees for applications. Previously in OpenGL, you could ask it, I want a 16-bit per channel texture. And OpenGL got to give you an 8-bit per channel texture instead. It provided no guarantees as to the rendering quality of your textures and render buffers. It got to just choose whatever it felt like based on your parameters you passed in. So in OpenGL 3, they actually say, if you ask for 16 bits per channel, we'll give you 16 bits per channel. If you ask for 8, you'll get exactly 8. This will help avoid applications running into silly bugs like we actually had one M-player was trying to use 16 bits per channel and then just stuffed its 10 bits of data in there without checking to see if it had space, resulting in crazy color banding as the top bits got dropped off. So this should help reliability for applications by actually providing them with the results they asked for. Another major upgrade is that we finally have access to floating point textures. You would think this is something that's quite obvious, and we agree, but it's a brand new feature in OpenGL. You can finally have floating point data coming into it. There's also guarantees on the precision of math in your shaders. Previously, there was some rough advice in the spec. Shader math, all the math in GL should be accurate to about 1 part in 10 to the 5th, maybe. That would be nice. Now we have some actual requirements. You have to support 32-bit integers, for example. Previously, the way a lot of implementations implemented integers was you would just put it in a floating point value and you would truncate after all your math. So now that we've finally got GL3, or now that tomorrow we'll finally have GL3, what's up next? We're hoping to spend about 3 months working on mostly just making the thing that we're shipping tomorrow actually as good as you would hope. So we're working on a bunch of performance work, fixing remaining stability bugs, and the one new feature we're planning on doing is multi-sample anti-aliasing. This is the feature that gives you smooth edges on your rendering applications. Generally, you get 4x anti-aliasing, which is much worse than provided by Cairo, but if you're used to jaggy edges, this will help with that. But the main thing we're talking about doing in the next 3 months is a lot of testing. This is what came out of our planning meeting. We wrote down a bunch of stuff we thought we might do on the board for features, then we erased it all. We came up with this list of what we want to do for testing. Mesa's testing story in the past has been pretty bad. Back about 3 years ago, when somebody was working on a Mesa driver, you would write some change, and you would run OpenArena and see if OpenArena still worked correctly. And if so, commit, you're good. We're changing that these days. Starting a couple of years ago, we have an automated test suite called Piglet. And now we can actually say, if I'm going to implement a feature, something new in EGL, let's go write a bunch of tests for it so we have automatic testing to make sure it works in the first place and keeps working as people hack on the system. So this is sort of the Piglet story here. Starting back in 2009, I think we had 67 tests for Mesa total. That was for everything to do with OpenGL. That was what we tested. And over the years, we've started to realize that everything that we weren't testing was always broken. So let's just keep writing tests every time something's broken, and hopefully at least that part will keep working. So the model of Piglet development, a lot of closed source test suites for OpenGL you run into take the approach of there's this feature and it's got a bunch of options to it. Ways you can run your shader, blending modes, your constant values that can be associated with it, all sorts of stuff. So we don't know what to test, so we'll just test all of it. Okay. You end up with these test suites. I think Intel's OGL conform that they use internally takes about 2 days to run to completion, if it doesn't hang your GPU in the middle. So for developers that are trying to turn around many changes per day, that's just not tractable. Nobody runs it. So Piglet's model is we want a bunch of small, isolated, short test cases that hit some particular feature, and then exit and move on to the next one. One of the advantages, actually, that we changed in the last year is that for these short, isolated tests, we now run them in parallel, lighting up all your cores to do testing as fast as possible. So over the last 3 years, we've upgraded from about 67 tests to now over 10,000. My regular runs run about 9,800 tests. And we have a 99.2% pass rate. So what I'd like to say here is, if you're an application developer and you have any bug to do with GL, please, please, please write a short test case, get it into Piglet, and we fix 99.2% of them. The other piece of OpenGL debugging change in the last year is the introduction of API trace. This is a project that came out of VMware. They're faced with the problem of, we have all these giant applications that people want to run under virtualization. And we have a driver that's supposed to render them, and we want to make sure that the driver keeps rendering them. So let's trace every command that goes through OpenGL, send it off to the disk, and then we'll replay it later. We'll capture all the frames in the first run, so we have all of what got rendered. And in subsequent QA runs, just make sure you keep rendering the same pixels. If something changes, somebody can go look at it. But make sure whole applications keep running reliably. So our contribution to API trace, Carl Wirth started a couple of months ago on this, I think. Our first reaction to API trace was, oh, this sounds really cool. But if I'm going to debug my driver, I'm still faced with about 5 seconds of NextWiz is a gigabyte of OpenGL commands. Mm-hmm. I don't want to go poking through there trying to find the one command that caused my problem. So Carl's been working on a tool called API Trace Trim. The idea is basically we want git bisect for these traces. So what he's done, he's got this program that you can run and take your trace and start chopping out your draw calls, right? Take my trace, cut out all the frames in the middle until that one frame that was broken. Once you cut that out, go cut out all the draw calls in that frame that didn't matter for the particular thing that was wrong. Once you've done that, cut out all those textures that aren't involved anymore. And so now I can have a bug in some application where previously to debug Neverwinter Nights, for example, I have to run this program, click through menu, see that the scroll bar is broken, look at my debug logs, and then go hack my driver and try to say, okay, I don't think it's this kind of texture anymore. Let's just ignore those textures and not draw them, and start the program again, click through the menus, see that my texture is still there and still broken. Okay, it wasn't those. Wash and repeat. Do this process over days. Now with API Trace Trim, I take the trace once, we cut out all the calls we don't want, and get down to create a context, bind the context, clear the screen, load a texture, draw that texture to the screen, exit. And our debug cycles now was down to, I think the NWN bug, once it got trimmed, was half an hour to fix because, oh, there's the bug right there. We're also looking at API trace for performance testing. A lot of applications out there that we would want to test don't provide some reliable replay mechanism. You know, you have a game that somebody cares about, but that game doesn't have a demo replay functionality that some games do. So what we can do with API trace is go ahead and capture that game, take that capture, build a C file that runs the game so that you can run it at native speed, and then run that through and measure the performance of it. Another cool thing we can do this way is there are some OpenGL extensions for monitoring performance counters. So the GPU actually has performance monitors similar to how CPUs have them. The trick is that you can't monitor those counters from the CPU because it's an asynchronous process, but you have to stick commands in your command stream to go monitor these counters. So with API trace, I have a trace of the application. I can go stick my counters in anywhere I feel like and measure things like how many cycles do I spend on this shader across the entire run of the application. So that's one of the places we're heading with API trace next. So over the 2D driver, things had settled down for a couple of years with the UX8 development where not a whole lot was changing. And things are getting exciting again. Chris Wilson has been working on a new acceleration architecture called SNA, Sandy Bridge New Acceleration. His goal with this project is we want to see how fast we can make the chip go. If we don't care about, you know, how easy it is to build or anything, we just want the fastest driver possible, what can we do? He's actually had some pretty amazing results with this. For years, the idea had been that you can't do GPU acceleration of the X window system faster than software rendering. We did do it because there's penalties to mixing software and hardware. So if you have a 3D application and X rendering, you still want to use hardware even though hardware is generally slower because you avoid the synchronization penalties. He's actually shown that you can run the hardware 4x faster than software rasterization. The downside is this was quite a bit of work, 70,000 lines of code for this new acceleration architecture. The previous one was 13,000 lines. In comparison, the entire 3D driver is 40,000 lines. So the 2D acceleration got kind of huge. This is not shipping at this point. It's a configure time option. We're still trying to figure out where we're going with this. So as sort of the exact opposite direction, Glamour was a little research project I started probably a year or so ago. The idea was I don't like writing X-acceleration architectures. I don't think they're that important. But I keep having to do X-acceleration because a new chip comes out with new 3D state, and I need to go write a new 3D driver inside my 2D driver, even though I'm also writing a 3D driver in OpenGL. So what if we just put X on top of OpenGL and see how fast we can make it? I kind of let this work slide for a little while because it wasn't really a priority. X isn't that much of our workload in terms of what people want out of us. But another developer has picked it up and has been continuing that. Glamour is now, from what I understand, faster than our current mainstream acceleration architecture. It's 226 lines in the driver, which I'm pretty excited by. And there's 10,000 lines of OpenGL code in a shared library that other drivers could make use of. It's still slower than SWRAST. We're not getting there at all yet. One of the concerns that's come up with these two new acceleration architecture options is, what are you guys doing? You just got UXA working finally. 2D was finally working. Why are you messing with it? I think they're right. I think we probably shouldn't be messing with it to the extent that we are. 2D is very hard to write. Our testing coverage of it is pretty poor. There's the X test suite, which is the core X operations. There's RenderCheck, something I wrote, that's a really, really awful testing tool that just tries to run every combination of render extension operations and see if they work out approximately right. It's very error prone and very inefficient. So yeah, we're very concerned about switching our entire acceleration architecture in one shot again, like we did with UXA, which took years to finish. So what we're hoping to come up with Glamour is, instead of tossing out all of UXA and plugging Glamour in its place, what if we take our current UXA acceleration and cut out a chunk of it? Say the X video, the taking YUV data and turning it into pixels on the screen. Take that part out, cut it out of UXA, plug in Glamour instead, and ship that. I think there's a lot of hope for doing this successfully. We would cut out a lot of driver code. As an example, the 965 video stuff for doing that video acceleration is thousands of lines, I think. So we might be able to make incremental progress towards OpenGL acceleration for X without throwing everything out all at once. Another piece of the graphics stack recently is CairoGL, which I talked about here at FOSDEM a couple of years ago. The idea here is, previously Cairo generates a bunch of trapezoids representing some complicated vector path geometry, ships it off to the X server, and the X server goes and carefully in software constructs masks for it, puts it onto the GPU, and the GPU renders with that mask. Instead of doing that, we could use our OpenGL acceleration, make these masks in software still, upload them to the card from a direct rendering context, and do our rendering client side. It means a lot less sharing of all the load inside of the X server that we have right now, so multiple clients could interact better, take advantage of multiple cores, and it would mean that there's a lot less pressure to do a bunch of X acceleration work when Cairo stops using rendering. The downside, as I'll say again, it's still not as fast as rendering in software. Nothing is as fast for doing Cairo currently, except for SNA, as using the software backend for Cairo. So what a lot of applications end up doing is, instead of using X at all, just render everything in software, and when they finally want to paint on the screen, go do an X split image of just dump all my image data to the screen. So I think there's still a lot of optimization opportunities in CairoGL. It was pretty dumb software when I wrote it. A bunch of people have been hacking on it since then, but we might be able to do better than software in the direct rendering mode. But the interesting new work going on in CairoGL is, some people have said, well, computing all these masks in software is really expensive, but I have MSAA hardware. I have 4x multi-sampling, and that would get me my smooth anti-aliased edges in Cairo to a quality that nobody's really going to notice the difference. And by doing this, I can emit my geometry as geometry instead of computing this mask in software of all my little trapezoids. So they're hoping to get much better performance out of Cairo than you can get with either the software backend or with what I did before for direct rendering. And this is, CairoGL is being used by the Wayland clients currently. We're hoping to make it usable for general X applications. We're talking about, getting used for GTK. So we're hoping to see Cairo actually take off performance-wise by taking advantage of this. But the downside is that we do have to go do MSAA for GL. libdrm. libdrm is a little piece of shared code that sits underneath the X server and the GL driver and libva. All it does, it manages these buffer objects containing graphics memory. So it's just an interface to the kernel ioctls, managing a user space cache on top of that, so that when you ask for a buffer, we give you a buffer you recently had instead of freeing it and remapping it. There wasn't a lot going on with it for a long time, and we were using it less and less as we stopped making so many separate buffers for objects in the GL driver. But what's going on now, we're taking advantage of this. Because the libdrm sees all of the graphics operations going down to the kernel, we can plug in a layer in the middle that takes all those graphics operations, saves them off to disk. The format for this is called OB files. It's a format used by the Intel chipset designers, actually. They use it as their testing format for keeping graphics workflows so they can run it against their software simulator. So we're actually making use of this now. We're taking our graphics workloads that aren't working for some reason, save them off of a file, and we can run it through a software simulator that, in addition to providing a bitmap of the output, also provides hundreds of thousands of lines of debug output that, if you can parse it, has the information you need for why your graphics don't work. It's paid off a few times. In particular, we're using it for new hardware development. So even before we get hardware in our hands, we can generate OB files for that hardware, run it through a software simulator, and get the new hardware up and running on day one. The other piece of debug code, we're finally doing our debug batch buffer dumping, or just taking your command stream and printing out what we sent off to the GPU in a pre-printed fashion. That's now available in libdrm for anyone. So that's the update on Intel graphics in user space. I'm wondering if anybody has any questions. Yep.
You were talking about Glamour. Now, some years ago, we had XGL. How does that compare? Because XGL already tried to do rendering through OpenGL.
Yeah, XGL was a really exciting idea at the time, but it faced two major problems, I would say. One is, at the time, we didn't have graphics memory management. So a lot of what XGL was trying to do is implement graphics memory management by, I have a screen of this size. I need to render my pixnap in it. Okay, I'll use this chunk of it to do some rendering, and then I'll use this piece of it for the next piece of rendering, this piece of it for the next piece of rendering, and if I need to evict something, I can go read it out and all this stuff. It's awful. Now we have graphics memory management. This can be a lot easier. The other piece of it is what XGL exposed. XGL had sort of a library interface, it's called glyphs. And it was trying to expose the render API as what the X server used for talking to GL. So it was exposing something that wasn't OpenGL for XGL to use to do GL operations. There were a lot of impedance mismatches there of, well, render isn't actually what hardware does. Does the X server want to talk render to the thing doing GL, or should the X server just do GL? So the Glamour stuff is very direct OpenGL access. If you want to do render, you write the OpenGL to do render. If you want to do Bresenham lines, go write OpenGL to draw Bresenham lines. Go do whatever you want, particularly now that we have shaders, right? We can do all of these crazy FB operations that were never accelerated before because you can just do integer operations in a shader, discard pixels or set pixels or whatever you want. So I think we'll be able to do a lot better these days because of the memory management and because we're not building a new hardware abstraction layer between X and the hardware. Yeah.
Question about the embedded hardware from Intel. Is there any, I don't know, they're using, I think, different hardware cores, and is there any outlook that there's going to be an open source driver?
So the SGX hardware?
Yeah, for example.
Yeah, I'm not aware of any changes on that. Although interestingly, some of that work for Glamour actually has been done by developers working on the closed source drivers. They were using an EXA-based 2D architecture, and they've totally tossed that, replaced it with Glamour for massive performance gains on their hardware. On the other hand, this means that Glamour development is being driven by SGX performance characteristics. So. Anybody else? All right. I guess thanks everybody.